Okay, so once again, good afternoon, everyone. I'm going to start the class. And first, I'm going to share my screen first. Okay, so I hope everyone can see my screen. Now we're going to continue last week's lesson. Okay. Okay, so I think I've discussed the three factors that influence ionization energies last week. There are three of them. I'm going to give like a sort of review. The first one is the size of the nuclear charge. The second one will be the distance of outer electrons, and then the third one will be shielding effect of inner electrons. Okay, so I promise that I will do question number 2 here. Here's like write the equations that describe these following here. So let's do that. So this is actually really simple. I'm going to stop sharing first. Switch my screen to image first. Okay. Okay. So now I'm going to annotate. So the first question is the first ionization energy of calcium. So we're going to do that. So the first one here, we have calcium. So basically ionization energy, since this is the first one, so we know this is calcium. So this is pretty simple to write ionization energy. This is calcium. And yes, okay. So this when becomes when it's become ionized. So now we'll leave at Ca plus because we kind of like subtract an electron of it, one electron. And this is close to one electron. There's a negative charge because electron is a negative charge. Okay. So basically this means that you take out one electron, forming a positive ion here for calcium. And this calcium right here means that if calcium in like one positive charge plus one electron, it will be equals to this calcium right here we have on the left-hand side. So this is what it means. First ionization energy means that we take out one electron. So now for the second question, we have the third ionization energy of potassium. So if we're talking about third ionization energy, it means that we have taken like 3 electrons from the element. So there are three like previous steps, but we're just like doing this third step, which is like the third ionization energy. So here we're going to have K, just write that, 3 plus. So this means like yet again, we're going to take one more electron from the potassium charge, which like previously is a 2 plus charge, and now it becomes a 3 plus charge, plus one electron equals to this. Okay, so that's for the third ionization energy. So it goes actually the same for like the rest, like what kind of ionization energy is that? So now we have the third question. We have the second ionization energy of lithium. So we're going to write the atomic symbol for lithium, which is Li here. So this is already plus because we're talking about the second ionization energy. It means that lithium has undergone the first ionization energy. So, okay, I'm just going to explain this again. So when the first ionization energy, it doesn't have, this element doesn't have any kind of charge. As you can see from calcium right here, it doesn't have any positive charges at all because it hasn't gone through any kind of ionization energy. But for example, here, as we can see lithium here, because it's like has undergone the second ionization energy, it has a positive charge already since it's basically the outcome from the first ionization energy. So here we have the plus charge. So this means here we have lithium, so plus E minus here means that another electrons be taken from this. So therefore, this is how we get this one. Okay, so this one actually plus this, it will be equals to this. So that's basically means. Now we're going to have the fourth question. It's actually the same process. I think you've already understand what this means. So the fourth one would be the fifth ionization energy of sulfur. So we're going to write down the atomic symbol sulfur first. And since this is the fifth, so it means the fifth year, this one should be 5 plus. So if this is 5 plus, talking about fifth, so this should be 4 plus. And here plus 1 electron. So there you have it. This is the fifth ionization energy of sulfur, second ionization energy of lithium, and then here's the third ionization energy of potassium, and this is the first ionization energy of calcium. So that's how you write the equations. So far, do you have any questions about the four questions here? So if you have any questions, just feel free to ask. Not then I will proceed to the next question. Okay. So I'm going to go back to the questions here. So I'm going to stop sharing again. I'm going to reshare the other screen. Okay, so for question number 2, I'm just going to explain this. Not really going through this a lot. So I think it's going to be important, but I think I can explain this again later in this chapter. Okay, so the second ionization energy of nitrogen is 2,816 kilojoule mole to the power of -1. The third ionization energy of nitrogen is 4,590 kilojoule mole -1. Explain why the third ionization energy is higher. Okay. So I want you to think about this for a while before I explain. Okay, so I'm going to explain the reason why. So there are actually a few reasons why the third ionization energy is going to be higher than the second one. So first of all, if we see the electronic configuration, so we know that I'm going to annotate again. So then say the configuration of nitrogen. So basically nitrogen is 7, has an atomic number 7. So meaning that the configuration would be something like this. So 1, S2, we have 2, S2, and then we have 2, P3. So basically 2 plus 2 plus 3, that would be equals to 7. So this would be the electronic configuration of nitrogen. Okay. So basically it asks us about nitrogen energy table. So basically after removing the 2 electrons, meaning that the configuration will change from this to something like this. I'm going to rewrite this again. So we have 1, S2, 2, S2, and 2, P1, since we have removed two electrons. So basically when we remove the electrons, that's from the stable one. So removing this third electron, as you can see right here, the third one here. So it actually destabilizes, meaning it's like kind of unstable in the structure. Like stabilize the structures, and this will make the element make the nitrogen, like it requires more energy to make it like more stable. So that's why removing the third electron will require a lot of more energy. So that's why it's like ionization energy is higher. So it makes sense, right? Okay. And this is actually like the consequences, like the subsequent of after removing the electronic configuration. Therefore, it will have a closer proximity to the nucleus. So after the third electron being removed, it will be closer to the nucleus, like the lower energy orbital. So let's say we remove the third electron. So it will only be one s2, two s2, and two p. No, we don't have this one anymore. We can just cross this out. So after removing the third electron, we only have one s2 and two s2. So this with this outer layer being removed, now it has closer to the nucleus. So it becomes closer, the nucleus becomes closer on a lower energy orbital, and this actually makes the force of attraction stronger. And once the force of attraction becomes stronger, it will have like it needs more energy to overcome this. So therefore, that's why the initiation energy will come higher. So do any of you have any questions about this? If there's something that you feel like I need more explanation, then I will try to explain this again. So do any of you have any questions so far? Okay, so if you have no questions, I'm just going to give like a sort of like short review. So basically, it means that when you remove like an electron, or like after what number of kind of ionization energy, when the outer layer is removed, then the number of the ionization energy here, it will become significantly high because now the electron, with the electron being removed, it will become closer with the nucleus. Nucleus is like the center of the atom. So this actually when this like thing become closer to the nucleus, the force of attraction will become stronger. So when the force of attraction becomes stronger, it requires more energy. So therefore, the anesthesia energy is also higher. So that's what I'm trying to say. So I hope you can understand this. If not, then you can just ask me questions, okay, about this sample here. Or you can just ask it through the chat box. I will read it during class as well. Okay. So I think we're done with number 2. But if you have any questions about it, then feel free to ask about question number 2. I can go back to the questions again. Okay, so I think we're done with this one from last week. So we're going to move on to this one here. So interpreting successive ionization energy. So here we have a graph. So figure 3.4 shows the graph of successive ionization energy against number of electrons removed from sodium for sodium. So here's a logarithmic scale to the base 10. It's just because the values of successive ionization energies have such a large range. So we have a graph of number of electrons removed along with the logs and ionization energy. So you can see like there's a significant jump in this one. This one is not so much. Okay, so we can deduce that. So I'm just going to read this, probably add my own explanation. Okay, so we can deduce the following about sodium from this one. So the first one, the first electron removed has a low first ionization energy when compared to the rest of the data. It is very easily removed from the atom. It's therefore likely to be long way from the nucleus and well shielded by inner electron shells. So as you all know that sodium has an atomic number of 11. And we also know that 11, like, okay, so sodium is from the alkali metal. So it's like from group 1. We all know that it tends to lose an electron to make it more stable. So it has like the same valence electron as neon, which is 10. So that's why it has a low ionization energy when the first electron is removed because, well, it is actually easily to be removed. Actually, it has the tendency to do so. That's why we have a like low ionization energy. But it quickly leaves to like it has a high ionization energy for the second electrons removed or second ionization energy because in this state, the electrons of natrium is actually stable, as we can see right here. The second electron is much more difficult to remove than the first electron. There is a big jump in value of the ionization energy. This suggests that the second electron is in a shell closer to the nucleus than the first electron. So if I draw the shell, so we have like 1s2, 2s2, and 2p6, and then we have 3s1. So with 3s1 removed, we have 2p6, which is actually closer to the nucleus. And the closer the electron is to the nucleus, then it will become harder to remove and therefore require a higher ionization energy. So from the second to the 9 electrons removed, there is only a gradual change in successive ionization energies. This suggests that all these 8 electrons are in the same shell. So as you can see, this one right here, 1, 2, 3, 4, 5, 6, 7, 8. So this 8 are in the same shell, which is 2. So we have 2s2 and 2p6, right? Because therefore it's like doesn't have that much of a big leap because it's the same shell, like the same, yeah, it's the same shell. That's why it doesn't have like the significant change in the ionization energies. So the 10 and 11 electrons have extremely high ionization energies when compared with the rest of the data. This suggests that they're very close to the nucleus, which is 1s2, which is like the closest electron to the nucleus. Like the lower the level of the valence electrons, it is like closer to the nucleus. So therefore, it also like requires an extreme amount of ionization energy. This suggests that the very close nucleus. There must be a great force of attraction. The closer to the nucleus, then the greater the attraction between the nucleus and these electrons, and there are no electrons to shield them. The large increase in ionization energy between the ninth and 10th electron confirms that the 10 electron is in the shell closer to the nucleus than the ninth electron, as you can see right here. This is the ninth electron, this is the 10th. It has like a big leap because they are in different shells. So this is the second shell and this is the first shell. And the first shell is actually the closest one with the nucleus. So as you can see right here, this is picture so that you can like picture this in your mind what I meant earlier. So this is the nucleus, which has like the inner circle, which has the number 11 on it. And then the outer layer here, we have 2 electrons, which is very difficult to remove because it is the closest one to like with to the nucleus is the closest one. So therefore it's very difficult to remove and it requires a lot of ionization energy. And then to that, we have the 8 electrons that is less easily removed. It's actually like harder, like more difficult to remove than the like 1 electron here. That's like at the very outer shell. It's like very easy to remove. So that's why it doesn't require a lot of ionization energy. However, the 8 electrons here on the second shell requires more energy than this 1 electron here. But it's still less difficult when compared to the 2 electrons that is closest to the nucleus. Okay, so do you have any questions about this so far?
No, Kak.
Okay, so if you have no questions, I can move on to the next. lesson. But if not, then okay, if not, I can move on. But if you have any questions, you can just feel free to stop. Okay, so I think we're going to think about this for a while. Okay, so I think I'm just going to pick like one of this question. I'm going to pick question A here. Okay, so we don't really have much time to discuss everything. Okay. So the successive ionization energies of boron are shown in this table. So we know that boron, okay, I think boron has 5 electrons, right? I mean, it's a number. Yeah, so boron is 5. Just trying to make sure. Okay, so the atomic number of boron is 5. So that's why it's like, so now we're just trying to, okay, so the ionization energy is trying to remove all electrons of boron. Okay, so we can notice that this from the first and the second ionization energy doesn't have that much significance, and so the second to the third ionization energy. But as we can see, the interesting part is that from third to the fourth. Okay, let's see here. Third to the fourth ionization energy has like a pretty huge leap from 3,000 to 2,500. Okay. So the question is, why is there a large increase between the third and fourth ionization energies? Okay, so we're going to try to write the electronic configuration here. 1s2 and 2s2 and 2p1. Okay, so like I said earlier, like the valence electron, like the very outer electron, because here we have 2p1. It tends to, okay, so boron tends to lose this electron here. So therefore, it doesn't require a lot of ionization energy. As you can see right here, it only requires an ionization energy of 799. So that's how. Okay, so this is the for the first ionization energy. So we're going to move on to the second and third ionization energy, which is 2s2 we have here. And it doesn't have that much of a gap, like doesn't have much difference, doesn't have like the significance and the significant difference between the first, second, and third, because this right here, the three outer valence electron, you can see it's actually 2, 3, right? So I just drawn that in this electronic configuration, as you can see right here from question part 2. Okay, so since the three outer electrons are in the same shell, which is shell number 2, it doesn't have that much gap between them. But when we are moving to the fourth electron, which is the one in the first shell, which is the closest to the nucleus. So basically the 2 here is the one that is like very, very close to the nucleus, meaning that it has like a really great attraction. Yeah. So that's why it has like, so that's why from this third to the fourth ionization energy, it has like a really big leap. Because moving on to the fourth ionization energy, which is in like the central near the nucleus, it requires a lot of ionization energy since like the greater the force of attraction, then the ionization energy required to remove the electron is also requires more energy. So that's why this like gap is explained. So that's actually the reason why. So explain how this figures confirm that the electronic structure of boron is 2,3. Okay, so basically this question number 2 is actually explained from this thing that I've drawn here. So I chose basically the same like the first one. So just take note that every like shell, so we have like 1, 2, 3 shell. So every shell that is being removed, then it will requires like there's will be like a difference, a large increase between the ionization energies. So for example, right here, the three first here, as you can see, here's three, which is the first three ionization energy here that has gone through by boron. It doesn't have a significant difference between among the three. So that's why we can confirm it is indeed 2.3. And now the fourth and fifth ionization energy doesn't have that much of big leap as we see from the third and fourth ionization energy, which means that these three, the first three belongs to the same level of an same level of like shell. So it belongs to the same level shell. And the fourth and fifth also belongs to the same level shell. So that's why we can confirm it's indeed 2.3. Okay. So I think that's all. Do you have any questions for this? So do you have any questions about this?
No.
Okay, so you all understand. And I'm going to clear first, and we can move on to the next one. So this is actually basically the same like this one. But this one it has already up the table, but we have to calculate it first. Okay, it will take a really long time. So I think if you understand the concept, you can do question B. So I think we can skip that. Okay, so here's a tip. So we can use successive Einstein energies in a way to predict and confirm the simple electronic configuration and confirm number of electrons in the outer shell of an element and hence the groups to which the elements belong. Okay, so here's our examples. Okay, I think you can read this. We're going to move on to the next part. Okay, hold on. Okay, so this is actually interesting. So we look for a large jump in the value of incision energy. So we're gonna see large jump doesn't, okay, 1 to 2, no, 2 to 3, no, 3 to 4, to 5, no, 6, okay. So the interesting one is from 6 to 7. Okay. Okay, this occurs between the removal of the 6 and 7 electrons. Yes, as we can confirm right here from 8,000 something to 27,000 something. So this is a really significant difference. So six electrons have been removed comparatively easily. So this six, the first six here. To remove the 7 electron requires about 3 times the energy required to remove the 6 electron. So there must be 6 electrons that are shell of X. So the element X must be in group 16 of the periodic table. Yeah, so you can look up in the periodic table and you know which electron have like the valence electrons of each. So in group 16, yes, it's indeed we have 6 valence electrons. So we know that the noble gas have 8 valence electrons, which is a full shell, which is like noble gases have like they're in group 18. And if group 17, which is the halogens, so group 16 has 6 valence electrons. From that we can know that yeah, in the group 16, since the difference is from 6 to 7, meaning that 6 valence electrons can be removed easily, meaning that we need to find a group that has 6 valence electrons, which is group 16. Okay, so now we are going to move on to this one here. So the first 6 energies of an element are this number you can see here, 1090, 2350, 4610, 8220, and 37, and 37. Okay. So we can see that the first 4 right here that I kind of like highlight there it doesn't seem that it needs like a lot of Einstein energy to remove the electrons. However, there is a huge jump between the fourth, okay, hold on, between the fourth and fifth ionization energy. It has a really significant difference from 6,000 to 37,000 to the 3,700. So it means that this element, this mystery element that we're trying to find, has four valence electrons. So note that here the significant difference. So I'm going to the significant difference is between the fourth and the fifth. So the fourth and the fifth ionization energy, it has a huge gap between them. So that means that you have the mystery element have four electrons, valence electrons. Okay, so we're trying to find a number that have four valence electrons, four electrons. Okay, so now we are asked that which group in the periodic table does this element belong to? So from the periodic table, you can all check your own periodic table. You can actually look up the periodic table. So you understand periodic table, then you already know that the group that has like four valence electron belongs to group four. So meaning that the mystery element they're trying to find belongs to group four, which is consistent since group four has a characteristic that they have four valence electron. So therefore, this element belongs to group four. So do you have any questions about this?
No.
Okay, so I hope all of you understand since ionization energy is not really that difficult, I think, since it doesn't require all like kind of like calculations or anything, just requires understanding with the periodic table. Okay, now we can move on to this part here. So the next part, we're talking about subshells and atomic orbitals. And I think most of you are familiar with this already from previous classes. So talking about quantum subshells here. So the principal quantum shells apart from first are split into subshells, or you can say sublevels. So basically, each principal quantum shell contains a different number of subshells. Here, so subshells are distinguished by the letter S, P, or D. There are also F subshells for elements with more than 57 electrons, but F is not really that common. Um, you should just use until D, as you can see right here. So for shell 1, as you can see, or you can say N1, only has one S. So 1s2, it only holds two electrons. And this one from N2, we actually hold this much. This is 8 electrons. So usually combined to N1 can hold up to 10 electrons. And so on. Okay. Here. You have actually another explanation. Okay, give me a moment. I need to take a drink. I want. So in any principal quantum shells, the energy of the subshell electron increases in the order S, P, and D, meaning that D is the largest, though the largest of them all is F. Okay. So the first principal quantum level, which is N1, holds a maximum of 2 electrons. And the second principal quantum level, N2, can hold a maximum of 8 electrons. So 2 electrons will be in the S subshells and 6 electrons will belong in the P subshell. And the third principal quantum level, N3, can hold a maximum of 18 electrons, 2 electrons in the S subshell, 6 electrons in the P subshells, and then 10 electrons in the D subshells. Okay, I'm going to give me more. Plus 14. plus, okay, give me a moment. Plus 10. Okay, this is N3. So we've already discussed N4. Usually, questions daily basis you will only fully find till level 3. But just so that you know that S can hold up to 2 electrons, P can hold up to 6 electrons, I'm sorry, and then D can hold up to 10 electrons, while F can hold up to 14 electrons. Okay, this is figure 3.6. You can see that already. That the order of subshells in terms of increasing energy does not show a regular pattern of S and P, then D after the element argon. Selection of subshells of the argon appears to overlap. So the next element of argon is potassium. Potassium oxide is in the 4s and not in 3D. So the first element electron in the 3D subshell is element 21, which is scandium. So when high-speed electrons hit gas particles at low pressure, those colored lines are seen through an instrument called a spectroscope. The S speed came from terms used to describe these lines as for sharp, P for principal, and D for diffuse. So as you can see right here, this is the order. So 1S, 2. So 1S, 2S, 2P, 3S, 3P. So instead of 3D, we have 4S first, and then we have 3D, we have 4P, and then we have 5S, then we have 4D. So basically like overlaps from after 3P right here, it will become overlap. I mean, it will overlap. Okay, so now we're talking about the atomic orbitals. So each subshell contains one or more atomic orbitals. So an atomic orbital is a region of space around the nucleus of an atom that can be occupied with one or two electrons. So each orbital can only hold a maximum of 2 electrons. Number of orbitals in each subshell must be S, 1 orbital, P, 3 orbitals, and D, 5 orbitals. Okay, yeah, I've gone too far. So here are some shapes of the orbitals. You can observe that. So I will not go too much about the picture. Okay, so filling the shells and orbitals. So the most stable atomic configuration, or the electronic structure, often is the one that has the lowest amount of energy. The order in which the subshells are filled depends on the relative energy. The subshells with the lowest energy, the first, is therefore filled first, followed by those that are successively higher in energy. So as we noted in figure 3.6, the one that I previously showed, the order of the subshells in terms of increasing energy does not follow a regular pattern. So here we have it. So 1S, 2S, 2, 2P, P, 3S, still normal, 3P, and then go to 4S, 3D, 4P. So it's kind of like an anomaly right there. Okay, so here we have question number 5. So this is actually easy. It's like the one that I've told you before. So I'm just going to write this down. So name 3 types of orbital present in the third principal quantum shell. So 3 shells, right? So we have the S orbital, the P orbital, and the D orbital. So that's the first one. So this is actually S, P, and D, what I've stated. We state the maximum number of electrons that can be found in the third subshell. So we're talking about third subshell. Meaning that we have 3S, 3P, and 3D. So we know that an S orbital can hold up to 2 electrons, while the P orbital can hold up to 6 electrons, and D can hold up to 10 electrons. So 2 plus 6 plus 10, that would be equals to 18. So the maximum number of electrons that can be found in the subshell, the subshell, the third quantum shell would be 18 in total. So I hope all of you can understand this part. So I'm sorry that I just erased that. real quick. But I think all of you can understand what I mean from that since I actually explained that in the last. Okay, so now we're talking about electronic configuration. Representing electronic configurations. A detailed way of writing the electronic configurations of an atom that includes information about number of electrons in each subshell is shown below for hydrogen. So as we can see here, this is the principal quantum number, which is 1. It has 1, this is level 1. So for quantum number is 1, and then number of electrons is stated here, the above here, above the subshell. It's usually number of electrons. So helium is 3 electrons, so it will be written as 1s2. So it has 3 electrons. Now we will have so the first, okay, I'm just going to read the explanation here. Lithium has 3 electrons, so the first orbital can only hold a maximum of 2 electrons. So the third electron must go to the next highest subshell, which is L2s. So the electronic structure of lithium would be written like this. So electrons are added one by one for successive elements, filling each subshell in order of increasing energy. So that the configuration of the first 18 elements are shown, table 3.5, as you can see right here, until argon. So this is actually really easy here. So for the configuration, atomic falling number. So for 16, we have it right here, like sulfur. So we written as 1s2, since it is more than, so 16 is more than 2, that's obvious. So after 2, it actually needs to go to the next highest subshell, which is 2. So therefore, we go to 2, and 2 subshell 2 can only hold up to 8 electrons. So 8 plus 2 is only 10. And we still have 6 more electrons to go. So this 6 electrons will go to the next highest subshell, which is subshell number 3. So therefore, we have 3s2 and 3p4. So that's actually the basics. So that's for sulfur or atomic number 16. So now we have 9, as you can see in floor here. So 1s2 can hold up 2 electrons. And there we still have 7 more electrons to go. And this 7 electrons all fit in the second subshell. With second subshell can only have hold up to 8 electrons and it's only 7. So it's still in the second subshell. So when S2, 2s2, and 2p4, it will equal, when S2, 2s2, and 2p5, it's equal to 9. 2 plus 2 plus 5, 9. So now we have 20 right here. So we know that after argon, or after 3p, it is not 3D, but it will go to 4s instead of 3D. So now I'm going to write the electronic configuration for, if it's 20 atomic number. So we have 1s2. So now the first subshell has been filled since it can hold up to 2 electrons only. And then for the next 8 electrons, it will go to the subshell level 2. 2s2 and 2p6. So far we have 10 electrons already being distributed. So now we're going to the third subshell. So we have 3s2, 3p6. So now we only have like 1, 2, 3, 4, 6, 10. So we only have 18 so far. So now the 2 electrons will go to 4s2. So it is not 3D, but it's 4s2. As you can see, that's like the order it's not that like structured after argon. So now we have 4s2. So now we're going to calculate 2 plus 2 is 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18, and plus 2, that will be 20. So this is the electronic configuration if the atomic number is 20. Or if you want to like make this more concise, people usually write only like the back of it, and people you use the electronic configuration of the noble gas. So as you can see, the first five right here, 1s2 up to 3p6, it's actually the same, like the like S is like the same as the electronic configuration of argon. So we can actually write the atomic number of 20 right here. For an element 20, we can write this as AR, meaning that it's the same as argon, the first few here. So we have AR here and 4s2. So it technically means the same. People will know that the atomic number of argon is 18, and here we have 2, so 18 plus 2, that will also be equals to 20. So this is actually the short term of how to write electronic configurations, and you can actually find this like on your periodic table. It's actually pretty common to write this since like if it's like a really long electronic configuration, it will take up much space, but if you write the closest noble gas, then it will become much more efficient. So actually you can write 16 right here by using the electronic configuration of neon. So as you can see here, this is neon, and this is the 16 right here. You can see that until up to 2p6 is actually the same. So we can write the configuration of sulfur, for example. We write this as Ne. So Ne has 10 atomic number, so 10. So we have an addition of other 6 electrons. So we can write this as Ne here, 3 as 2, and 3p4. So 10 plus 2 plus 4, that would be equals to 60. So this is a short way to write this instead of writing it like this. So it saves much space and time as well. So do you have any questions so far about writing electronic configurations?
No, Kak.
Okay, so if you understand, I'm going to go on to the next. Oh yeah, actually you can see it right here actually. Okay. Yeah, like what I've said here. Okay, needs to clear my drawings first. Okay. So electronic configuration of potassium, for example here. So potassium's electronic structure, we have 1s2, 2s, 2p6, 3s2, 3p6, 4s1. The other electron goes into the 4s subshell rather than 3d subshells, like I've actually previously explained. So filling the 3d subshells, after calcium, a new subshell becomes occupied. The next option goes into the 3 subshell rather than p4. So scandium has the other configuration of this one, like I've said previously. So it's argon right here. So because argon has the same, like this one right here. Okay, so it's argon, right? So this is the atomic configuration of scandium. The scandium is 21. So we have argon here, and this will become 3 additional one. So 18 plus 3, that will be 21. Okay. So this is because the electron occupied the orbital with lost energy to the 3d subshell is just above the 4s subshell, but below the 4p subshell. So this begins a pattern of filling the 3d subshell ending with zinc. So zinc has an electronic configuration of this. So the chromium and copper, the electronic configurations of chromium and copper do not follow the expected pattern. Chromium have the electronic configuration of Ar3d5 4s1 rather than the expected Ar3d4 4s2. So copper is the electronic configuration of um 3d10 4s1 rather than expected 3d4 4s2. So you will have to learn that these two elements are exceptions to the pattern. So this is our exception. Sometimes it can be a little bit confusing, but usually when you start learning about like periodic table, then you can start remember about the exceptions. But yeah, usually for beginners, they don't have this kind of question, so don't worry about it. So get into Krypton, the electron add to the 4p shells because this is the next house. Okay, so there's just more to it. So we're almost like it's almost time of the class. I'm just going to give here the next of electron configuration. So this is the anemoid that we're talking about, the um copper and chromium. So usually they're not much anemoid like this other one like zinc and everything. They actually follow that pattern except copper. You probably expected to see like 4s2 3d9, but nope, it is actually 3d10 4s1. And same goes to chromium instead of 3d4 4s2, we 5 3d5 and 4s1. So these two are anomaly. And yeah, you can see that since the noble gases, there's like closest to them is like argon, so therefore they're like writing argon, argon, argon for like a diff one. So you don't have to like write this lengthy kind of electronic configuration. It just makes things neat and simpler. So therefore, you just write the closest one. And then you can write the additional one. For example, potassium has atomic number 19. The closest noble gas electron would be argon, which is 18, so 18. So we have like an additional electron, which is force 1. So we're just going to write 18 plus 1, so argon is force 1. So it's still like equals 19. So I think this is going to be easy. So kind of easy questions with this one. Okay, so vanadium. So that would be 4s2 and 4s2, then we 3d. Okay, hold on. So there'll be argon. So I'm gonna write the first example here since we still have time. So there will be argon. I'm just gonna write with vanadium. Probably the rest I'm going to give to you guys as homework. Probably next week. I'm not gonna give it this week. So VAR, so this 18. This is the anomaly starter. So instead of 3D here. Okay, hold on. So we have 4s, right? Yeah, just trying to make sure. So we have 4s2. So usually the write is like this. So 4s2. So we have 20 so far. And 3d3. So this will equals like 18 plus 3 plus 2. Okay, hold on. Yeah, it's 23, right? I'm going to like double check usually. So yeah, the outside configuration of vanadium is indeed argon here, which is 18, and 3d3 plus 2, which is like to sum up the additional electrons, which is like 5, so 18 plus 5 to 23. So I hope you can understand. So since this will be like the end of our class, we have 3 more minutes. Do you have any questions that you'd like to ask me about today's lesson?
Okay.
Okay, so if you have no questions, I'm going to stop sharing my screen. And I'm actually going to stop the recording as well.